Welcome back to COIC 2325. This is part 3 of chapter 6. So in this lecture, we're going to be looking back at bitmap sets and just doing a little review and more talking about why we use bitmaps. And then we're going to look at conditional loop instructions and conditional structures. So let's see first, let me see if I can grab the pointer here. Okay, I don't know if the pointer is going to record, but this right here is an example of a bitmap. So this looks like, just like a normal binary number, except it's not a binary number. Each bit is mapped to something. So bit 0 right here is mapped to, let's say, if we look at the E flags register, the very first bit of the E flags register is mapped to a flag, and the next one is mapped to another flag, etc. And we don't know what they're mapped to. We don't know, if it's if the 0 flag is here, but we know that they're in there. We know that they're mapped, and whoever built the assembler knows where they're mapped, and that's their job. And when we have a flag, like let's say the 0 flag, we know that we clear it by assigning it a value of 0, and we set it by assigning it the value of 1. And again, that 1 and 0, deciding what sets it and what clears it, is up to the programmer who makes this bitmap. So we're going to treat it like an array. And so this right here, where we have bit 0 would be mapped to like array sub 0. And then bit 1 and so on and so forth. Except, when we're looking at a bitmap, bit 0 is actually on the right-hand side. So, but it's just called a bit vector or a bit array. And in this next slide, we see the bit array or the bit vector of the E flags register. So we have, starting with bit 0 of the E flags register, this is where you can find the CF flag. So the control flag is here. And then in bit 2 is where you find the parity flag. To find the sign flag, you have to go to bit 7. Now, we don't have to worry about this as the programmer. We just use these flags. We check the flags, and we use like conditional jumps depending on how the flags are set. But we don't have to worry about what position they're in. But they are mapped to something. So bitmaps, in this example, the bitmap is used to store these different flags that control that are set by different instructions. And bitmaps can be used for all kinds of things. So let's take a look at, in the next slide, some examples or some uses of a bitmap. So we can use a bitmap in low-level memory management. A bitmap sets can be used to keep track of allocated and free memory blocks. each bit would represent the status of a memory block. So maybe a 1 could mean that that block is allocated, and a 1 could mean that that block is freed. And that depends on how the programmer decides to do that. We could use a bitmap for device input-output. So, for example, it could be used to control and monitor the status of input and output devices. Each bit may represent a specific device, like let's say bit 0 could represent a printer. Or bit 0 could represent, let's say that bit 0 represents the printer, then the 1 and the 0 could represent the state of that device, like is the printer on or is the printer off? So 1 could mean on, 0 could mean off. Permissions and access control. So in an operating system, bitmap sets are used for managing access control permissions. Each bit can correspond to a specific permission. Like if we set or if we set the permission, it means that they are able to do XYZ. Clearing means they can't, or the other way around. So setting or clearing bits determines whether a user or process has that permission. Configuration flags. So this would be each bit can represent the presence or the absence of a particular feature or configuration option. And then arrow handling. Each bit may correspond to an arrow code. And it could also be like, let's say that bit 0 is the printer, maybe that bit could represent if there's an error with the printer or not. So it could be, 1 tells you there's an error, 0 means there's no error. Just, it's whatever you want to actually map your the bits to. So what we looked at in, I don't know if it was the previous I think it was the very first part of, the first part of 6-1. We were looking at ANDing and ORing and exclusive ORs, the XOR, NOT, and we use the AND and the OR, etc., to manipulate these bits and to look at these bits. And today we're going to introduce some new things, and we're going to review that because we're going to have to review it. We're going to be using it to be able to do loops that are dependent on these flags that are set by the compare instruction that we looked at. And we're going to review the different jump instructions, and then look and see how we implement if-else statements in assembly. So when we look at the just as a review, when we look at the bit map set, we have something that's called the set complement. And the set complement inverts all of the bits by using NOT. So remember, if we had 1 1 0 0 and we said NOT 1 1 0 0, that is supposed to say NOT, even though it does not look like it, then this would just change this to 0 0 1 1. So that is called a set complement, and it just inverts all the bits. Pretty simple. Set intersection refers to an operation that finds the common elements between two sets. So here's a set X, and set X gets moved into EAX, set Y then gets ANDed with EAX. So set X and set Y get AND. And when we do an AND, what we're going to look at is what are the common elements between the two sets. Data that needs to be compared, filtered, or processed in some way to find the common elements or shared characteristics between the two sets of data would require a set intersection. So just as a review, here's an example. If let's say that set X was 1, 1, 1, 0, and set Y was 1, 1, 0, 1, and we do an AND, then our result is going to be false and true is false. So a 0 and a 1 is a 0. A 1 and a 0, true and a false, is false. Because with an AND, the only time that it can be true or 1 is if both bits are 1. So this is 1 and 1, and this is 1 and 1. So what this shows is that the only two bits that are common between these two sets, common elements, like it says right here, is bit 2 and bit 3. Remember, we start counting at 0. This is bit 0, bit 1, bit 2, and bit 3. So we could see that those are the only two that are common. Okay, let's erase all this and go to the next slide. So then we have the set union. And set union, it combines the elements of two sets into a whole new set. So we have set X and set Y, and we're going to combine those, and we're going to use the OR to create a whole new set. So again, let's say that set X has 1, 1, 0, 0. And then let's say that set Y has 1, 1, 1, 1. Okay. Let's make one of these a 0. Let's make this one a 0. Okay, so we're doing an OR, and remember when we do an OR, and also in the previous one, the AND, this EAX will actually get the result. So whatever result I write here, EAX will have that result. So that means that this number is going to go away right here because it's in EAX right now. So with an OR, everything is true unless both bits are false. Both bits are 0. So 0 or 1, so 0 or true is true. The only time you can get a false is if both bits are false. And then this is 1 and this is 1. So what this has done is we've combined, and everything that had a 0, so if you had a 0 and then you had a 1, then it took a 1. If they're both 0, they stayed 0. They're both 1, they're going to stay a 1. So it combines both of them into a whole new result, and it gets put into EAX. So it gets combined and it gets put right here. So that's called a set union. Oh, it's always done with an OR. So let's look at conditional loop instructions. And we had to review that because we're going to be using this in our loop instructions. Before we start looking at loop instructions, let's review. So these are the loop instructions that we're going to look at, loop Z and loop E. Loop Z is loop if 0 or equal. These two instructions are the same. Not Z, not equal are the same. We're actually going to be using these. So loop equal actually loops if the 0 flag is set, and this is if not 0 flag set, not equal. Before we do that, let's look at compare and review the compare instruction, because we're going to be using this through our examples. So if we're looking at the destination and the destination is less than the source, then the 0 flag is cleared and the control flag is set. If the destination is greater than the source, then the 0 flag is cleared and the control flag is cleared. If the destination is equal to the source, then the 0 flag is set and the control flag is cleared. So just remember, 0 flag is always set if the destination and source are equal. Otherwise, they're going to be cleared. Okay. Okay, so here's how the loop Z and loop equal instructions work. So when you have a loop, remember that the ECX counter is the one that keeps track of how many times you're iterating through the loop. So you have to set that ECX counter, and it has to be greater than 0. And then every time that we iterate, when we get to the bottom of the loop, that ECX automatically gets decreased by 1. When we call loop Z, that subtracts 1 from ECX. If ECX is greater than 0 and the 0 flag is set to 1, then we jump back up to the loop and we iterate again. So we keep iterating if ECX is greater than 0 and CF equals 1. So this loop is useful when scanning an array for the first element that does not match a given value. If it matches a given value, then the 0 flag gets set to a 1. And it gets cleared when we're comparing and it doesn't match the given value. Loop not Z or not E, so not 0 or not equal. Again, it works the same way. We have the ECX counter, we got to set it, it decreases by 1 every time. If ECX is greater than 0 and the 0 flag is equal to 0, then we're going to jump back up to the top of the loop and iterate. So this is useful when scanning an array for the first element that matches a given value. And we're going to take a look at an example of this one, of using the not Z and not E in the next slide. Okay, so loop NC example. The following code finds the first positive value in an array. So here's our array. It has negative numbers and positive numbers, and we're trying to find the very first positive number. We have a variable that's called Sentinel, and we'll talk about what we use this variable for at the end. But basically, it's if we don't find a positive number, then we're gonna point to 0, okay? Which means we didn't find a positive number. So the first line here it moves the address of the first element of the array into ESI. So ESI points to where that negative 3 lives in memory. ECX is going to hold the length of the array. So this array has 2, 4, 6, 8 elements, so ECX is 8. That means that this loop that we're going to look at in just a second, loop NZ, iterates a maximum of 8 times. Got to go through all the elements. So we start here. We have a label called next. we test the very first number. Remember, when you put ECI in brackets and you're saying word pointer, it means give me the value that I'm pointing to by ECI. So it gives me the value of -3. So let me get a pencil here. So this here represents the number -3. Okay, grabs that -3 there. And then we're going to test it against this hexadecimal number. Now this hexadecimal number is equal to this binary number here that I have on the right hand side. And what this is doing, it is testing to see if this number -3 is a negative number. Now test, if you remember, is the same as the as anding something, except it does not affect the destination. It doesn't change the destination. And changes the destination. This doesn't change the destination. We don't want it to change the destination. So if we know that we have a negative, if we look at a binary number and the least significant bit is negative, like let's say we have this number here. This is the least significant bit. This bit is a 1. We know that this is a negative number. So if we take this negative number and we AND it with, I'm going to use the same thing here, except I'm going to make it smaller, okay? So it's just going to be 4 bits, 1 0 0 0, just to make it easier. If I AND it with 1 0 0 0, then 0 and 0 is 0, 1 and 0 is 0, 0 and 0 0, 1 and 1 is 1. So my result is going to be a negative number. And what happens with the ANDing instruction is that it clears and it sets some flags. So if you look in your book and you look at the AND instruction, or you just Google and say what flags get set and cleared by the AND instruction in MASM, you'll see that the sign flag and the 0 flag get set and cleared. And there's some other flags that I'm not committing to memory. But here, because this is a negative number, then the sign flag is going to get set. And it's going to get set to a 1 because this is a sign number. And what that tells me is that -3 is a negative number. Okay, my 0 flag is going to be set to 0. And you can run this and take a look at it. So what I want to do now, because those flags are set, I want to push my flags to the stack, and I want to save them in the stack because I'm about to do an add, and you know that an add can affect your sign flag and your 0 flag. So you don't want anything to affect your flags because you've set them. And so we push those flags to the stack. We are going to now do an add, and when we do the add, what we're doing is we're adding to the ESI register, and that all that does is it takes us to the next number, to the -6. It moves us over to the -6. Because type array is the size of the array. So our array's word size, and remember that word size is 2 bytes. So we're going to add 2 to ESI and get us to the next element. So now we're at 6. We're pointing at 6. So let's see here. We're going to point, grab a color. We're going to be pointing here. Then the next step is we pop our flags, and we've saved the flags that were set by this test. And then we're here at the loop not 0. So is the zero flag set? No, the zero flag is not set. Why is the zero flag not set? Well, we're looking for the first positive integer and we haven't found it. We got a -3, sorry, got a -3. So the zero flag is not set, it's at 0. So we're going to go back up to next, and now we're going to test the -6. The -6 is going to set the same flags. It's going to set the 1, it's going to set signed to 1 and 0 to 0. So we're going to loop again, and then we're going to do the -1 and then the -10. When we get to the 10, we're going to test the 10. And what the 10 is going to do, the +10, is it's going to set the sign flag to 0. I'll just put just so it's faster. And it's going to set the 0 flag to 1. Okay? And because we set the 0 flag to 1, that means that this is a positive number. Now, why was the 0 flag set to 1? Well, let's just take a look at what a positive number does. If I have a number like 0, 1, 0, 1, this is actually a positive number. In decimal, this is a 1, this is worth 1, this is worth 2, this is worth 4. So this is a decimal number 5. If I AND that with 1, 0, 0, 0, I AND it. 1 and 0 is 0, 0 and 0 is 0, 1 and 0 is 0, 0 and 1 is 0. So my result is all zeros. And because it's all zeros, the 0 flag gets set to a 1. And this loop stops if the 0 flag is set to 1. And instead of going to next, it's going to go to this instruction. And this instruction says, jump if not 0. So our 0 flag is not set. So we don't go to quit, otherwise we would quit here. We actually go to this instruction. So our what we do now is we're going to set ESI to point to this 10 right here. And the reason is because at the end of this loop, ESI is pointing to the 30. And I just want to go back and point to the first number that was a positive number. So this instruction, all it does is it takes me back to the 10. So go ahead and type this code, run it, try to understand it. I want you to look at the flags as they get set, and so see when test sets the 0 flag, the sign flag, and the 0 flags, depending on if it's a negative or a positive number. Here, what I want you to do is see if you can figure out the code that locates the first non-zero value in the array. And if none is found, let ESI point to the sentinel value. So if you get to the end of this array and there are no non-zero values, then have it point to this sentinel value. So try to do that by yourself. The answer is actually in the next slide. So here's the answer, but try to do it by yourself. You can pause this and try to work on that. The next thing we're going to look at is conditional structures. So we're going to look at how to create if statements in assembly language, and how to create a compound expression like if this and that, or this or that. And The last thing that we'll look at is while loops. So here is, on the left-hand side, here's how we would do in C++ or Java an if statement. So if OP1, OP1 is equal to OP2, then assign 1 to X, else assign 2 to X. So if this is true, X is 1. If this is false, X is 2. Here on the right-hand side, we're going to do the same thing in assembly. First, we're going to move OP1 to EAX. We're going to compare EAX to OP2. We don't know what's in OP1 or OP2, but if they're equal, remember when we compare to the destination and the source and they're equal, the 0 flag gets set to 1. Okay? And jump not equal works off of that 0 flag. We don't have to remember that, but it does. So if these are not equal, up 1 and up 2, then we're going to jump to L1 and we're going to change X. We're going to move 2 to X, same that we did here. If these aren't equal, we move 2 to X. If these are equal to one another, then we're not going to do this instruction. It actually goes to this instruction and it assigns 1 to X. Once it assigns 1 to X, it jumps to L2 and just does whatever comes after that, the rest of the code. Okay, so this is how to implement this in high-level language. So here it's asking you to implement the following pseudocode in assembly language. So if EBX is less than or equal to ECX, you would assign 5 to EAX and assign 6 to EDX. So remember, you're going to use the compare instructions, and you're going to jump if less than or equal to. So you're going to find what is that jump instruction that checks to see if it's less than or equal to. So it has to do something with below. There's above and below. So there's the code, but I want you to see if you can do it on your own, okay? So pause the videos, try to do these on your own before you look at the solutions. Here you're going to implement this. So if less than or equal to var1 is less than or equal to var2, assign 10 to var3, else assign these two values. So stop the video, see if you can implement it, run it in Visual Studio, and then come and look at the solution. So let's take a look at how we do a compound expression. Remember, in high-level languages, if you have an and this first expression is false, we don't have to check the second expression, right? Because if the first expression is false, it doesn't matter if this is false or true. This is going to be a false statement because you have an and. So if the first one is false, nothing happens. But if the first one is true, then we check the next one to make sure that it's true. If they're both true, then we assign 1 to X. So here's how we do, here's one way to do that compound expression with and. So first we compare A and L. If AL is above, JA means jump if above, meaning is it greater than. So is AL greater than or above BL, jump to L1. So if this is true, what it does is it now has to compare these two. So it compares BL and CL. And if that's true, if it's above, then it jumps to L2. And it moves 1 to X. So this means it's true, it's greater than, true, greater than, move 1 to X. If it's not above, so if AL is not greater than BL, it doesn't do this line, JA line, it jumps to next. Because remember, if this is false, no need to check this. We just go below. There's nothing to do below. So we jump here to next. Again, make sure you understand this. I understand it, but you probably don't because I'm the one explaining it. So make sure you're understanding exactly what's going on here. You can replay this or go look at the JAX. What you want to do is go look at these instructions. Jump above, just so that you understand what's happening, what it's checking for. This is another way that we can do the compound expression, except we're going to do it with less code. So it says we're doing it with 29% less code. So first what it does is it compares AL and BL, same thing as before. And what we're going to check for is jump if it's below or equal to. So we're going to, here at this point, we're going to quit immediately if it's false. So if AL is below BL, then we're quitting. If not, it just goes to here and it compares BL and CL. And once it compares it, it says, okay, is it false? If it's false, it's going to quit. It's going to go to next. If it's not false, it's going to move 1 to X. So here it's asking you to implement this code. So this is C++ or Java. If EBX is less than or equal to ECX and ECX is greater than EDX, do this. If this is false, there's nothing to do. So go ahead and try to implement that by yourself, and then you can look at the solution. Here's a compound expression with OR. So with OR, if this is true, we don't have to look at the second expression. Automatically, this OR statement is all true. So if the first expression is true, we assign 1 to X. If the first expression is false, then we do have to look at the second expression and check to see if it's true. If it's true, 1 gets assigned to X. If the second one is also false, then we do nothing. Here's how they implement it with the fall through logic, which is the logic that is has less instructions. So make sure you type this in and you understand this code. Okay, this is how we do a while loop. So a while loop is really an if statement followed by the body of the loop. So this is an if statement, right? We're checking, is EAX less than EBX? If it's true, we're going to do this. And then we go back up. Is EAX less than EBX? If it's true, we do this. So we have an if statement, and we keep doing that if statement until this becomes false. So a while loop is really an if statement followed by the body of the loop, followed by an unconditional jump to the top of the loop. So here's a possible implementation. We compare, just like we're comparing here, EAX and EBX. If it's false, we're going to exit the loop, right? If this is false. So this is what that does. If it's false, if EAX is not less than EBX, it goes to here. It jumps to the next statement and exits. Now what this says is above, so JAE, above equal. So above means greater than. So if EAX is greater than or equal to EBX, then we're going to stop. Does that make sense? So it's the opposite. If EAX is greater than, above, or equal to EBX, then we quit. Otherwise, we increase EAX. So this line here is the same as this line right here. And then we jump to the top. Boom. And we keep doing this until this becomes false. So once EAX is no longer less than EBX, once EAX is bigger than EBX, then we're going to quit. And EAX, it's going to be bigger than EBX at some point because you're incrementing EAX by 1 every time. So here we're asking you to try this out. Implement the following loop using unsigned 32-bit integers. So this is a loop as you would see in C++ or Java. And what you want to do is write it in assembly. Okay, so try that out and then look at the answer. And that's the end of this slides. I do want to remind you that you can go ahead and do your discussion, and you can actually start your lab assignment. We've covered everything that each problem is requiring. If you have questions on any of that, please let me know. Send me an email, and I can help you figure out, what instructions you're needing for each one of those. So do the discussion, do the lab. Make sure that you practice these where it says take your turn and do it, because that's how your exam is going to be. So your next exam, you're actually going to have to code, and you're going to be asked to, to write some loops and to write some code that looks like this. Okay? All right, guys. Happy coding in assembly. Thank you.